So, in this video we're going to learn about refraction and the refractive index. You'll have come across refraction in P1 and it can produce some strange effects. So my recent fun-filled holiday in the tropical isle of Scarborough produced this holiday snap, all caused by refraction. So light, as you'll remember, travels at a speed of 300,000 kilometers per second in a vacuum. Okay. As it enters more dense medium, okay, the speed of light will decrease. So here we've got the vacuum. Here we've got water. Now, if you think about a vacuum, there are no particles in there. If you think about water, it has a lot more. Well, it has particles. Okay, although they're not that dense. Be denser than air, but not as dense as a solid. So, and then we have perspex. Perspex is a plastic solid, okay, and you can see it's much denser. Okay, the particles would be packed together, and as such, the speed of light decreases in that solid. This change of the speed of light is called refraction. And as it changes speed, it also changes direction, and this happens when it goes from one medium, okay, which is the substance, to another. So for example, here we have water and air. The light from the coin travels up until it hits the air, where it speeds up, okay, because air is less dense than water. When it does that, it moves away from this imaginary line we call the normal line, and it's at 90 degrees to the surface. Okay, so it produces these strange effects. If you've ever looked in water, you'll notice things look a bit weird. You try and pick something up, you don't actually guess where it is, and it's because of this. We assume light goes in straight lines when in fact, okay, it doesn't. In this case, it goes in a straight line and then it changes direction. So we think the coin is here, in fact the coin is here. Okay, so if we have a look at the classic science experiments, we shine in an incident ray of light, which comes along here, like that. Okay, notice we always put an arrow on. You lose marks if you don't have an arrow. Okay, you've got to show the direction of the light. It then changes direction as it hits the interface. Now, when it goes from a less dense to a more dense medium, it bends towards that imaginary normal line, and you should always put that on. Okay, so that's a 90-degree line. Okay, then when it goes from this more dense medium to a less dense medium outside, okay, it then bends away from that imaginary normal line. Again, showing my arrow. Now you can see we've got two angles we need to be aware of. Okay, we've got this one, okay, called the angle of incidence. So that's there. And we've got this one called the angle of refraction. That is a terrible way to write refraction. That's much better. So what you would do in order to do this experiment is shine light in, measure the angle of incidence, measure the angle of refraction. Now these two things are linked. So as you can see on this slide, as you shine the light in, ooh, cheeky, no arrows, it bends, okay, and it changes direction again, and we've got an incident angle of 69 degrees and a refracted angle of 39 degrees. Okay, so that would be here and here. Okay, incidence, refraction. The angle of incidence and the angle of refraction allow us to work out something called the refractive index, which represents how much light slows down when entering a substance. Okay, so here you can see something like water, 1.33, a denser substance like glass, 1.5, and then a much more dense substance like diamond, 2.42, which is why you get that kind of sparkly effect on diamonds. Ooh. And this is how they're linked. So the refractive index equals sine, and that's some maths, I, so the sine of the angle of incidence divided by the sine of the angle of refraction. Okay, so you're going to have to use your calculators for this. Okay, the proper calculators. And it's called Snell's law. You don't need to know that. And it's not related to Miss Snell. Andrews. So using my values from the previous slide, I've got an angle of incidence of 69 degrees, an angle of refraction of 39 degrees. I then use my calculator to work out the sine of 69, which should be 0.934 to 3 decimal places. And I then work out the sine of 39, which is 0.629, again to 3 decimal places. Then I divide 0.934 by 0.629, and I get a refractive index of 1.484. So therefore, if you think back to the previous slide where the refractive index of glass was 1.5, if I'd not rounded up to 3 decimal places and been lazy, I probably would have come out with 1.5, i.e. what we've got here is glass. Okay. If you then take another value from the same material, so you could have, I just had a look, oh dear, you could have 33 degrees and 21 degrees. Okay, and if you work that out, and that's what you're going to do now, okay, no slacking, then you should come to a very close approximation of our original refractive index. Now, what you might have to do, because you are very bright students, is to work out something that is not just a straightforward calculation, i.e. you're going to have to rearrange the equation. So, let's say the exam board are cheeky and they give us the refractive index of 1.5, and they give us the angle of refraction, but not the angle of incidence. So we have an angle of refraction of, let's say, 23 degrees. Okay, we need to work out what the angle of incidence would be, i.e. this value. Okay? So what we do is some basic maths. So if I'm dividing by sine 23 on this side here, then what I can do is times both sides by sine 23, and that will get rid of that. Okay? And we'll get sine 23 times 1.5 equals sine of the angle of incidence. So I work out this side first, and I do sine of 23 times 1.5, and that gives me a value of 0.586 equals sine I. Now usually you'd be amazed and you'd think, woo, I've finished. But you've got a little bit more to do, because that's the sine of the angle of incidence. We've got to get the angle of incidence on its own. Okay, so you're going to use a little button on your calculator called sine to the -1, inverse sine. You'll probably have to press shift and sine to use that. And we are going to inverse sine 0.586. And that gives a value for I, angle of incidence, of 35.9 degrees. Now, looking at the information that I originally used, I know that that is right. Okay, so if it comes into the glass box at 35.9 degrees, okay, the refracted angle should be 23 degrees. Okay, so we have got that right. Well done. And I think that will conclude what we need to know about refraction and the refractive index.